All right, good morning everybody. We are your first UT Design project. We are part of the Senior Design 2 team. My name is Yusuf, this is Patrick, this is Christopher. I'm a computer engineer, as well as Christopher's a computer engineer, and Patrick is an electrical engineer, and he worked on the hardware side, and me and Christopher led the software design. So the title of our project was PV Monitoring Solution with Wireless Communication. We were sponsored by Texas Instruments. This project was used to enhance the in-house solar panel system that Texas Instruments has. We were tasked with two parts of the project, which divides into hardware and software. The hardware part was led by Patrick, and we were tasked with redesigning an existing circuit board in order to improve accuracy, to add a temperature sensor module, and to make it compatible with the solar panel connectors that they already use. On the software side of things, that was led by Christopher and I. We were tasked by establishing a wireless communication network between the circuit boards. We did so by programming a client-server module in Kentucky, as well as being able to read accurate values from the ADC, which include current, voltage, and temperature. I'm going to hand it off to Patrick to talk a little bit more about the hardware design, and let's get things going.
So as Yusuf mentioned, one of the important design goals was to make the design compatible with Texas Instruments' existing PV system. This was achieved by giving each of the PCBs its own enclosure, which doesn't require any special mounting or placement. Also connected to the PCB are solar cables, which are terminated with MC4 connectors, which are the connectors that are commonly used in PV systems. Our other design goals included maintaining the maximum input voltage of 90 volts, also increasing the maximum input current from 10 amps to 15 amps, adding the temperature sensor for within the enclosure, another temperature sensor for the solar module itself, as well as improving the accuracy of the previous voltage and current sensors. And the brains of the board is Texas Instruments CC2538 microcontroller. Microcontroller converts the data that is measured, and then it utilizes the onboard antenna to wirelessly transmit the data to another instance of the PCB. And Christopher will detail the software.
So on the software side, TI didn't give us a real starting point, so we were able to just choose our own path that we wanted to take as far as the architecture of the software. And like Yusuf said, we chose a client-server model, and we used Kentucky NG, which is an OS that kind of runs on the microcontroller. We used it as a basis so that we could have easy wireless communication between the boards, and it also allowed us to read the ADC values and convert them into useful values like the voltage, current, and temperature. And that's really it for our presentation. So, any questions?
How much heat is dissipated inside the sealed enclosure?
We haven't been able to test it within the enclosure itself because our power supplies don't have the MC4 connectors. But whenever we tested it just in open air, we don't feel any heat coming off the board itself.
Why are you worried about the voltage and current and temperature for the PV cell itself?
Well, one advantage of our design is that it monitors the solar array at the module level. So you get to monitor each individual solar module. And being able to monitor each individual module, you can see if one module isn't performing as well as another module. So especially with the temperature sensor, say you have two modules that are neighbors with each other, and both modules are reading about the same temperature, you can make the assumption that they're getting approximately the same level of sunlight, but if one has a much lower power output than the other one, you can assume that the lower output module is not functioning properly. You can troubleshoot better.
How many watts is a module?
Texas Instruments hasn't given us the detail on the exact wattage of the module. They just told us that they wanted to be able to measure a maximum of 90 volts and 15 amps. They also informed us that they don't expect it to ever reach the maximum.
Yeah, that's 1,350 watts.
Mm-hmm.
I mean, watts of power.
Yeah.
That's about
It is.
And how many modules are typically in a system?
Texas Instruments hasn't informed us exactly how many modules are in their system, but this is scalable. You can have theoretically as many of the PCBs as you want on the modules, all wirelessly transmitting to one central module or one central PCB.
And some of your wireless is in some sort of mesh network?
Yeah, it uses the 802.15 protocol. as opposed to 802.11, which is normal Wi-Fi. And you can have as many client boards that are connected to solar modules as you want, all sending data to a single master node that's connected to a computer, and that's where the data is processed.
So did you test that at all, or you just had one or two? Or?
We tested 2 clients with 1 master. We don't have the setup to test more than
Usually
that.
you get over 600 when you have problems. Yeah.
Okay, yeah, we don't know how large TI's solar array is, unfortunately.
You mentioned that you have a goal of not increasing costs more than $2 a board, and yet the only number I see related to that is that you have $300 for the prototype. So did you do any estimates of what the price of the board, the cost, basically the BOM would be for volume production?
We weren't tasked with seeing if we're going to sell this because this was only supposed to be used for in-house by Texas Instruments. So we don't know if they want to outsource this, if they want to be able to sell it on a commercial level. So we weren't tasked with being able to deal with the sales side of things. We were just more focused on making it work with the hardware and the wireless network.
It's not you have a stated goal in your slide here of $2 a board. Did you do any measurement against that?
To expand on that, I think that's saying not increasing the price of the old design by more than $2 compared to the new design. Not that the new design
So
is
the
going to
old
cost
design
more.
was $298?
No, this is only for a prototype. Keep in mind that the more boards that you order, the
I'm
lower
being
the cost
facetious
is going to
somewhat,
be.
but I'm just pointing
Okay.
out that you didn't show any results related to that particular goal.
Understood.
So were you a design or prototype team for a TI design that they sell online, or is this an internal tool?
They don't sell the design online, but they do have the original design posted. It's open source.
And follow up, doing this design, what was your what major problem did you guys encounter, and how did you guys get around it?
I wouldn't say the hardware had too many hurdles. The software had more hurdles. Is there any specific thing?
One of the problems we had with the software is because we chose to use Contiki NG, it's very undocumented. So you have to just try things and see if they work. If they don't work, try something else, see if it works. One of the problems we had though was that the op amp on the board that we had from TI was actually bad. So no matter what we tried, we were getting wrong values. That took up a lot of time, and after many troubleshooting steps, we realized that it is the op amp that's bad, and fixing that made the code go quite smoothly.
You've got a design goal of -4 degrees to 164 degrees. Was that tested? And if so, how?
It wasn't fully tested, but that -4 degrees is limited by the temperature sensor itself. That's as low as it can measure. The 164 degrees is just how high we can go before it hits the 3.3 volts that is the maximum voltage input to the ADC.
Folks, let's thank the group. Thank you.